Bismillahirrahmanirrahim and Assalamu alaikum. I am Faisal Omar, your chemistry teacher, and today we are going to study a new topic. It's about hybridization. Okay, first of all, let's see what's hybridization. In chemistry, it's a kind of process when two different kind of orbitals they combine with each other to form newly hybrid bond orbitals. The newly born or the newly made orbitals will be known as hybrid orbitals. Normally, when we hear the word hybrid, it means that it's a kind of species which comes from two different species. Okay, so it will have the properties of both parent species. So in hybrid orbitals, it's still like this, and if we study new hybrid orbital, it will resemble a little bit to the parent orbitals. Okay, now we are going to study the hybrid orbitals. Actually, there are three most important hybrid orbitals that we study in school level. The first one is sp orbital, the next one is sp2, sp3 orbitals. But I've introduced a little bit about sp3d and sp3d2 orbitals. Let's start with the sp hybridization. Actually, sp hybridization involves with the mixing of one s orbital and one p orbital. And when they mix with each other, they form two hybrid orbitals, which are known as sp orbitals. Let's have a look at the diagram. This is the s orbital, this is the p orbital with two lobes. When these two combine with each other, this process is known as hybridization, and sp hybridization, they form two orbitals, sp two orbitals. Okay, one sp and the other one is also second sp orbitals. And if we study in a molecule, it will have a something like this shape, and they will have a linear geometry. Let's study with an example. Example is the beryllium. The electronic configuration of beryllium is 1s2 and 2s2. 2p is 0. There is no electron in the 2p. Okay, so let's look at the ground state of the beryllium. This is the first shell, this is the second shell. In first shell we have 1s2, 1s orbital which will have 2 electrons, and second shell there's 2s orbital with 2 electrons, and 2p is empty. There is nothing in the 2p orbital. So when this electron gets excited, it can go up to the higher one, the 2p1, and then it will become 2s1 and 2p1. But beryllium has two bonds, which means that each bond of them should be in same energy level. So what should be done in this one? Right now it cannot react, because if it wants to react, the p has a higher energy and s has a lower energy. So this is a kind of difficulty. So what happens, these two orbitals mix with each other and they form two hybrid orbitals, which are known as sp hybrid orbitals. Now beryllium can easily make two bonds with the help of these hybrid orbitals. And let's have a look here. The reaction of sp hybrid orbitals of beryllium with 3p orbital of chlorine. Beryllium is in the center and it has two hybrid orbitals ready to react, and chlorine has one p orbital ready, 3p orbital ready to react. There's also 3p orbital ready to react. So what happens, they react with each other and they form beryllium chloride. The angle between them is 180-degree angle. Let's study the next one. It's the sp2 hybridization. In sp2 hybridization, 1s and 2p orbitals combine with each other and they form three sp2 orbitals. You can see one here. This is the s orbital and these are the p orbitals. When these three combine with each other, they form three sp2 orbitals, 3 in number. Okay, so it will have a shape something like this. It will have kind of trigonal planar geometry. Let's study with the example. The example is about the boron. The electronic configuration of boron is 1s2, 2s2 and 2p1. This is the ground state of boron, and we have seen that boron makes 3 bonds. Right now, if we look over here in the ground state of boron, the boron has only one orbital able to react. Okay, 2p orbital. So what happens? How can it make 3 bonds? Actually, this one electron of the 2s2 orbital gets excited, and it goes up to the p orbital. So overall, now there are 3 orbitals, but their energy levels are not same. So what happens? The 3 of them combine with each other to form 3 sp2 hybrid orbitals. They are 3 in number. All of them have same energy, and now they can form 3 bonds. Now, if we study over here reaction of sp2 hybrid orbitals of boron and 3p orbitals of chlorine to form boron trichloride, you can see boron has 3 sp2 orbitals and chlorine come with 3p orbital from each side, and now they have formed boron trichloride. The angle between them is 120 and the geometry is linear geometry. Okay, students, let's go for the third one. The third one is sp3 hybridization. As is obvious from its name, one s and 3p orbitals combine with each other and they can form 4 in number sp3 orbitals. You can see over here s orbital, p and p orbitals. Now they have combined, they have formed sp3 orbitals. They are 4 in number. Okay, they will have a geometry something like this, and the angle between them will be 109.5-degree angle. Let's work upon an example. The example for sp3 hybrid orbitals or sp3 hybridization is carbon. Actually, carbon can also make sp2 hybrid orbital and sp hybrid orbitals as well, but we are studying sp3 for right now. So electronic configuration of carbon is 1s2, 2s2 and 2p2. In ground state, it has a shape something like this. But when one of this electron gets excited and it goes up to the empty orbital of p, now there are 4 orbitals. So what happens? These 4 orbitals combine with each other and they form 4 sp3 hybrid orbitals, all of them with same energy and same shape. Okay, but let me tell you something. In sp orbital, the share of s orbital was 1.2 and share of p orbital was 1.2 as well, 50-50%. But in sp2 orbital, the share of s orbital was 1 by 3 and the share of p orbital was 2 by 3. But in sp3 orbitals, you can see the share of p orbital is much more higher. It's 3 by 4 and the share of s orbital is 1 by 4. Let's have a look at this one. It's an example. It's a methane molecule. Carbon has sp3 hybrid orbitals, 4 in number. Okay, this reacts with the hydrogen, which hydrogen has 1s empty orbital. When they react with the hydrogen, they form methane, and the electronic geometry is over here is 109.5. It's written 109.28 as well. They are close to each other, so they have a tetrahedral geometry. This was sp3 hybrid. Let's study sp3 and sp3d hybridization. As obvious from its name, in sp3d hybridization, 1s, 3p and 1d orbitals combine with each other and they form 5 hybrid orbitals. All of them are known as sp3d orbitals. This is an example. It's the molecule of phosphorus pentachloride. So you can see there are 5 regions of electron density, and this means that the 5 bonds are made up of sp3d hybrids. And if we look over here, the structure over here is trigonal bipyramidal structure, and these are the bigger lobes of the hybrid orbitals. There will be other smaller lobes as well at the opposite direction, but it hasn't been shown in the picture for clarity. Okay, the next one is sp3d2 hybrid orbitals. In sp3d2 hybrid orbitals, 1s, 3p and 2d orbitals combine with each other. They are 6 in number, which means that they will make 6 hybrid orbitals. So all of them will be known as sp3d2 hybrid orbitals. Okay, this is an example of sulfur hexafluoride. Sulfur has 6 bonds with 1 fluorine. So which means that this 6 bond comes from 6 sp3d2 hybrid orbitals. And over here we can see that this shape is octahedral shape, and these lobes are the bigger lobes of these hybrid orbitals, and the smaller lobes are at the opposite sides. For example, smaller lobe of this one will be on the other side, but it is not clear because it hasn't been shown over here. Okay, as a summary, let's have a look at the arrangements, region of electron density, which are actually bonds, and hybridization. This is the first one. It has 2 bonds or 2 regions of electron density. Arrangement is linear geometry, and hybridization is sp 180-degree angle. The second one has 3 bonds, and the arrangement is trigonal planar. It's sp2 hybrid orbital and 120-degree angle. The third one is sp3 hybrid orbital with 109.5-degree angle, and it has a tetrahedral shape. Will have 4 bonds or 4 regions of electron density. This is the number of bonds that is formed between the atoms. The fourth one is sp3d2 hybrid orbitals. The angle between them is 90-degree and 120-degree angle. You can see in the shape. Okay, it's trigonal bipyramidal, and it will have 5 bonds. The next one is the octahedral. Octahedral, the bond, the number of bonds will be 6, and the hybridization is sp³d², and the angle between them is 90-degree angle within the all bonds. Okay, students, at last, let me tell you some important things, the ideas that you have to understand for hybridization. The first one is hybrid orbital doesn't exist in isolated atom. In single atom, hybrid orbital will not exist. To be exist, for the hybrid orbitals, they must react and form covalent bonds. So during this reaction, during the forming covalent bond, hybrid orbitals can be formed. The next thing is the shapes of hybrid orbitals are totally different from their parent orbitals. For example, sp hybrid orbital will not resemble totally to the s orbital or for the p orbital. Okay, they have shared their similarities and they have formed a new hybrid orbital. The shape will be different. And the next thing is that a set of hybrid orbitals is generated by combining atomic orbital. Okay, so atomic orbital must be combined to form hybrid orbital. The next one is the number of hybrid orbital in a set is equal to the number of atomic orbitals that were combined to produce the set. For example, for sp3 hybrid orbitals, 1s and 3p took part, which means that 1s and 3p make 4 orbitals. So as a result, the hybrid orbitals will be 4 in the number. The next one is all orbitals in a set of hybrid orbitals are equivalent in shape and energy. Let me give you an example of again sp3. We had 4 in number sp3 orbitals, so all of them will have similar properties and energies with each other. The last one is hybrid orbitals overlap to form sigma bonds. We have studied in sigma and pi bonds that hybrid orbitals always form sigma bonds, but pi bonds are formed in unhybridized orbitals. Okay, students, this was our today's lesson. If you want, you can repeat the video again from beginning until the end. And still, if you have any question and suggestion, you can write in the comment section below. I will be waiting there for you. See you next time. Goodbye.